Hello, good people. Hopefully we are live. Let me know in the chat if you can hear me or you can see what's on the screen. Some technical difficulties today. I'm 3 minutes late. Let's have a look how many viewers we've got. Okay, let them build up. How are we doing? Oh yeah. Okay, excellent. Well done, good people. All right. I had a moment there. That's all. Some technical difficulties today. Surprising surprise. We're good though. We're good. Welcome to the A2 Computer Science Revision live stream for Component 1. Are we all ready for our exam? We all feeling good? Nope. Oh dear. Oh my goodness. That's it. You know what? I'm wondering if a few old students, alumni of computer science will join us today. Let me get cracking, people, because we've got a lot to cover in a short amount of time. There will be breaks today, so I'll put breaks in between so we can get our sort of cognitive load to calm down for a second. If you look on your screen, you can see the A2 Component 1 topics, people. Do you know what the yellow ones, does anyone know what the yellow highlighted ones are? Yellow highlighted ones, anybody? Do you know what they're for? Now, I will warn people, apologies if I cough, I am not 100%, but I'm here, people. They're not the mock topics. They're not the topics that we are covering either. These are the topics that came up in 2024. Now, you might have seen on our coursework classroom today, I put up my analysis of everything from 2017 all the way up to 2024. I will also say that the last sorting algorithm was, in the 2024 paper, was the insertion sort. And also, the 12 marker at the end was all about the effects of computers on the nature of employment in computing. You will get a 12 marker. That last 12 marker in 2024 came in 1.9, which is economic, moral, legal, ethical, and cultural issues related to computer science. Now, you know what, people? I have leveled up here. What, are you ready for this transition? I hope it works. Oh yeah. Did you see that? You like that transition there, people? This is the 2024 paper, and you can go through that and have a look. However, what I have done for you, which I will move to in a second if I just transition over like this. Let's have a look at the next slide. This is what you asked me to cover. Now, what you're saying here is these are all the topics. 22 people responded to my Google form. These are the ones that people want me to cover. The ones in red I am not going to cover in this live stream because, people... Did I say 2024 before? Apologies. 2023. I do, yeah. My bad. The green ones are Component 1 topics that people asked me to cover. The red ones are what you asked me to cover, but they are in Component 2. So in the next live stream, if the people want it and the people wish it, we'll have a Component 2 live stream. I'll cover those ones in there, right? If there is anything between now and your exam that you want me to cover, that I've not covered in this live stream, then all you got to do is email me. Component 2, if you want me to cover anything in there that I've not got on the screen there, just, again, email me and let me know. I will cover what you want me to cover, okay? Do go on Google Classroom, do go on the coursework and have a look at the Comp 1 tracker that I've got on there because it'll help you out. Some people noticed it because I got a few emails. Now there is some exam questions based on all these things that I can go through towards the end. I will move through each one of these as quickly as I can. But what I've just realised is I probably need to know what these topics are so that I can go through them one by one. So first, we'll start off with translators. Okay. Now, translators covers program construction, which is further down, which is the compilation process, compilers, interpreters, and assemblers. That they are translation systems, aren't they? So if I just go back for a second, all right, and we look for where is it? Translators. Okay, program construction. Let's start here. Now I'll move through this extremely quickly, people, so I can get onto the exams. The exam questions are going to be more important for us a little bit later on. Now what we're talking about is someone messaged me and said, what is the difference between high and low level languages? We're currently dealing with 4th and 5th generation languages, with 5th generation being artificial intelligence. Our 4th generation is what we program in, so we've been doing Python. That's around a 4th generation language there. But high level, the highest level we can get is English language, and that's what me and you communicate in, all right? Further down you go, you get down to assembly, machine language or machine code, and then you get hardware there, which deals with the zeros and ones and things like that. With translation programs, you've got 3, compilers, interpreters, and assemblers, and they are all types of translators. And we use the term translators because it converts code or source code from one form into another. Now your compilers, they convert all your source code at once into machine code, okay? Compilers are very good because they compile once into one standalone executable file, and there's no need for any further compilation. Once it's been compiled, it is done. Machine code finished. And that means you can just put it on a USB stick, put it on a CD, email it to someone, and you can run it many times, providing that the architecture of your computer is the same as what it was compiled for. All right. By that I mean, if I make a Windows system or a Windows program, it needs to be ran on Windows. It's not configured or compiled for Apple, for example. And that's good because it protects the intellectual property. Interpreters are great because they are flexible. As long as you've got an interpreter installed on your machine, then you can run interpreted source code. All right. Now, what it does is instead of doing it as one file, it translates each line of code line by line. And the interpreter itself, like Python idle, all right, if you ever use that at secondary school because your secondary schools hate you, that is an interpreter. You can run it on any platform, which is great. It's what we use it for. All right. Now, remember, interpreted languages have some benefits. So line by line is great because we can see it, we can debug it better, and we can sort of figure out the logic a little bit easier. All right. And we've put there, interpreters are used for a number of languages, such as the ones that you might be used to. So in order to run them, you have to have it installed, and it can be run on any system, which we've mentioned. Now, we've got some advantages. My advice is you're probably going to be asked to compare these two, compilers and interpreters. They usually come as a pair. So be prepared to give me the advantages of interpreters over the advantages of compilers. I said all those before, so I'll quickly skip on. And we've got some disadvantages. What's the bad things about interpreters? You've got to have it running on a computer in order for it to be able to run the program. And source code needs to be compiled each time. Every time you run it, it's got to be reinterpreted. So that can run quite slowly. And you've got to rely on the interpreter for what we call machine level optimization. So basically live, you're going to optimize your code. Now remember, in the compilation process, not the interpretation process, in the compilation process, we have a stage for optimization, don't we? So remember that. It's quite important. All right. Someone has asked in the chat. It is a good point, actually. You keep putting your questions in the chat, and I will do my best to monitor everything across my 8 screens here that I've got in front of me. AI considered a visual language. Not quite visual. Non-procedural, probably, I would say. Because, remember, it's making its own assumptions. So grammar checking, language models are probably non-procedural languages. All right, that's the paradigm for them anyway. Okay. There is a little summary for you with the compilers and interpreters. I break them down into three distinct areas. The source code, so what's the source code for a compiler and interpreter? Multiple platforms, and distribution. Okay, now assemblers, bear in mind, assemblers just convert assembly code into machine code, right? The process is called assembling. We're not looking at assembly language in component 1. That comes in the component 2 paper, and some people have asked for it, and I will do some assembly language questions in component 2 if you wish for me to continue with my live streams. I didn't mention, people, but this is the last ever component 1 live stream on the Eduqas exam board. We are moving exam boards. What a shame. What a shame. So yeah, you're the last lot. Okay. Now assembly, it's very good. It's very quick. We use it in very low level things like my washing machine, for example. My washing machine, yeah, that uses assembly language, and it converts as a one-to-one or direct mapping. One-to-one might remind you of databases. Yes, one-to-one relationship, people. All right. But yeah, one-to-one just means it's got a direct mapping. So the ADD command, the add command, or the SUB, the sub command, or the LDA, or the STA, or the HLT command in assembly just has a specific binary number for it. That's all. Okay. So there we are. Yeah, said that before. Good. Right. So translating. It's a two-phased approach that happens when we are assembling code, but we're getting bogged down here into how assembling works. I don't think you need that level of detail, but the reason why that's in there is because when we teach this, we don't want you to get confused between a symbol table here, okay, and a symbol table when it comes a little bit later on in the compilation process. All right, we don't want you to get confused at these two at the moment. All right. Yeah, we are doing games next year for coursework. Yes, we are. We're doing it in Python. Yes. Okay. Just remember, machine code is not a very good system to write code in. We don't do it in machine code anymore because it's prone to errors and it's a nightmare. When converting assembler to machine code, you use an assembler, and you use a compiler and use an interpreter depending on what it's for. The exam question could just say to you, oh, well, this person needs a system to do this, this, and this. What translator would you recommend for this specific need? And you have to then give your opinion. Okay, your opinion. So this diagram here explains, you've seen this in lessons probably, but it explains the different types of translation that we have between compilers and interpreters. You can see that the top line up there is dead straightforward, right? When you are interpreting, providing you've got an interpreter installed, you will literally just jump straight to machine code and carry on. Now, when you write source code, a translator, such as a compiler, will turn your code into something called object code. All right, object code is just you writing your code and it being sort of semi-compiled, I suppose, but it's object code because it's not complete code until you add your libraries. So these are the things where you import. You might have done that in Python before, import something like a random class, for example, or some specific library that you want to use, and then this process here, the process between the object code and library, that has to be embedded in there, and that's the linker, the linking process between that. Once it gets to that stage there where you've got your library in there, you can just create your standalone executable file and carry on with your life. Okay? Or what you can do is you can have your intermediate code, so your halfway house, your in-betweeny code. And these things here, does anyone know what VM stands for? Whack it in the chat, people. Make sure you're still alive and kicking. What's a VM? Yeah, you need to improve your typing speed, people. What is a VM? There we go, they're all coming through. Visual media. Waleed, are you... What on earth? It's a virtual machine. Okay, a virtual machine is just an operating system that runs on a different operating system. So, for example, I'm running a Windows operating system and I run a Linux window inside the Windows machine. That means I can pretty much use any software I like. Very, very good virtual machines. But in order to run code, as in my Linux code, it needs to be intermediate code, then interpreted by my virtual machine to pretend it's Linux on my Windows operating system. Crazy. Hey, Linux is on a lot of systems across the world, yeah? You've probably used it before and you don't even know it. Yeah, you do need to know about virtual machines? Yes, you do. All right, that's an example of a virtual machine. So you can see there's a Apple operating system there, and it's running one of the greatest of all operating systems. Yeah, that's Windows XP. I do enjoy Windows XP. We can reminisce about that another time. All right. Yes, indeedy. Okay, so we skip on a little bit past those. Just remember, a virtual machine is just an interpreter. It takes intermediate code and runs it like normal. All right. We said all this stuff. Let's skip through. Now, does anybody want to know about the stages of the compilation process? Yes, okay, I can hear lots of people saying yes, good, right? Compilation process. They don't ask you about the interpretation process, people. They just ask you about the compilation process. We start off with lexical analysis. Lexical analysis, if you looked at a lexicographer, it's someone that studies words. Same thing with lexical analysis, people. Same thing. So let's delve. Let's delve, shall we? Here is a piece of code. You've written your piece of code. Oh, I'll tell you where you can find this document a little bit later on if you hang around. This piece of code here needs to be broken down into parts or tokenized. Tokenized. During the lexical analysis, what you need to do is you need to basically remove all the white space and unneeded punctuation. Right? All gone. Boof, get rid of it. Then you turn the remaining code into tokens. Remember, you can get a mark at any one of these stages by saying you will produce an error if it doesn't work. At any one of these stages, if you come across a problem, you cease compilation. You stop what you do. The computer sees no point in going any further because it knows your code is faulty and it will not work. So you produce an error at any one of these stages. All right. So that's my code, and that's it been tokenized. It's split up and broken down into parts. You can see the little boxes, I hope, where it's split down. If you can't see those boxes and it's blurry for you, you need to upgrade to 1080p, people, or 4K, but I'm not broadcasting in 4K at the moment. All right. Okay, symbol tables. Symbol tables. This is an A2 thing that you need to know about. So we create a symbol table or a dictionary. Now, a symbol table is broken down into two tables, what we call a reserved word table and an identifier table. They have a very subtle difference, and I've not seen one of these in an exam question for an awful long time. So, during syntax analysis, we look at what the code actually is and whether it complies. So, we create this reserved word and identifier table, which I'll show you in a second. The tokens of the code are checked to see if they fit the grammar. The grammar. As soon as you hear the word grammar or natural language, you should be thinking about Backus nor form. If you've looked at the predictor or the tracker on Google Classroom, you will know that Backus nor form pops up an awful lot. Most years, Backus nor form is on that paper. If you can master Backus nor form, you will be laughing. You'll have at least 6 marks in the bag, maybe more. After you've checked to make sure the grammar fits, then you create something called an abstract syntax tree. But again, if it doesn't fit, we produce an error message. Here is a piece of code. Classic exam question. Below is a segment of source program that is to be compiled. There's your code. Construct a reserved word table and an identifier table. So we need two tables that could be used to translate this segment of code into a stream of hex tokens. hexadecimal. Pop quiz. What base is hexadecimal? What base is hexadecimal? Answers in the chat. Oh, Atta's first in there. Well done, sir. Well done to you, sir. Very good. Oh, look at this, people. Good. All right. Excellent. Base 16. Right? What is base 16, remember? Base 16. Can I have a pen, please? Give me my pen. Give me my pen. Good. Right, so you've got A to F, right? And you've got 1 to 9. Or you can have 0 as well, I suppose. But A is 10 all the way to F, which is 15. All right, base 16 works in 4 bits, 1, 2, 4, and 8. If you add all of those together, what's your maximum? It's 15. All right, that's just a little sidetrack. That remember, binary doesn't come up till component 2. So component 2. Right, so let's make this reserved word table. Let's make it. Okay. Right, there we go. So, reserved word tables. We have 2 columns. One, the reserved word, and then the second column is the hexadecimal token. Now, the hexadecimal tokens, questions that I normally get, John, does the hexadecimal token have to be a specific pattern? No. As long as it's unique, you will get the marks. What about your identifier table? Well, your identifier table has an extra column, which is the type, and that's the data type of that variable. Okay? Now, how do we distinguish between an identifier table and a reserve word table? That's a question I'll throw out to you lot. What is an identifier table and what is a reserve word table? How do I know the difference? What goes in identifiers? What goes in reserve word? You tell me. I think I know. I hope. Get typing, people, get typing. What is the difference? Identifier, reserve. No. Data type column, yeah, that's the difference, but where do they come from? Reserve word is like all the Java components and then identifies the variables. Reserve word is like the code. Syntax and identifiers the variables and stuff. Interesting. Now the things, put you out your misery, people, right? The things that go in the identifier table are what you create as the programmer. The reserve word is what's already defined by the language itself. So for example, input. Input is already defined by the language. For example, Python, right? Equal symbol. Well, I don't create the equal symbol. It's already a part of my reserved words in the language itself. The plus symbol, yeah? The asterisk, the output, right? They are created by the language. I can't change them. I can use them. But the identifiers, basic cost. I make that. I make the basic cost. I make VAT. I make total cost. Okay? That's why I have to specify the data type of them. And then I give it a random hexadecimal token. All right? So that's the key difference. We have a type in the identifier table and you make those. The reserve word is by what the user creates. Oh, sorry, what the programming language creates. Let's not get confused there. All right. Now, with this as well, I said before about Backus-Naur form. One typical thing that students get wrong, and you probably did have it as an exam question, right, is the fact that what happens if you get something like this and... Oh, I'm pressing a button. That's wrong. What happens if I get brackets like this? Brackets. Now remember, brackets aren't created by me, so they'd be a reserved word, and you'd have to declare the open or the closing bracket as individual reserved words, and you would assign them 6-1, 6-2, whatever, right? So some students on one exam question I've seen put the open and closing brackets together. No, they are separate entities. Bear that in mind, people. All right. Now, I saw some people use regular expressions in their coursework. What the hell is a regular expression? It does a similar job to Backus no form. It checks to make sure that you've followed the rules of the language. The rules of the language. So, for example, I can't say, actually, what about input, speech mark, open bracket, close bracket. That is incorrect because the regular expression will say you can't have letters followed by speech marks followed by brackets, for example. That's the rule. You've got to follow it in this language, therefore not allowed. So we use regular expressions for that kind of thing. And there's loads of them. Now you're not going to be expected to write regular expressions in your exam. All right? Not going to be expected. And you don't need to talk about automator or state machines either. So I'll skip on. Semantic analysis. Semantics. Semantic, oh my goodness. You know what, right? If you write your pseudocode, I'm going to find you if you do this, right? Let's take variable 1. Variable 1. And you will say it is greater than or equal to variable 2. Yep. Happy with that? Anyone spot any problems? No, you don't. What about, believe it or not, I see this in second year computer science as well sometimes. What on earth is that? You might use that some other places, but don't bring that round here. Don't bring that near me. What on earth are you doing? That's called mixed mode arithmetic. You're swapping around the relational operators, and that is not allowed, people. You've got to follow the rules of the language. You can't just make stuff up. Another thing. Oh, this is recent. This is recent, you bunch of donuts, right? I won't name names. I won't bait people out here, right? Even though I really, really want to. This as well. What? What are you doing? What is that? How about climb into a bin? Because that's terrible. We don't do that, right? Remember, we're not writing mathematical notations here, people, so bear that in mind. All right. Now, semantic analysis checks that all the variables are declared and used, and it checks that the real values are not being assigned to integers. For example, real values, so floating point values being assigned to integers, whole numbers. If we assign a real number to an integer, it's going to chop off the decimal point and you're going to lose accuracy of your number. So it checks that's not happening because that's bad. And it checks that the operation is legal. So no mixed mode arithmetic like I just explained. Okay? Now in your exam, you can say as well in semantic analysis, then reverse Polish notation will be used. Now we don't teach that on the specification anymore. You can say it in your exam if you remember it, but it's not going to be expected. It'll be on a mark scheme, but it won't be expected because we don't teach anymore. Okay? Now, once the string of tokens has been generated, the syntax analyzer part of the compiler checks whether the sequence of tokens is in acceptable order. Okay? Now, here's 2 tokens. So we've got a variable equals a constant. So can a constant go into a variable? Right? Well, let's have a look. If my constant was 10, equals is that, variable there, so that would be 10. So that 10 would be assigned into there, no problem. Okay? Constants can go into variables because you're using them. Yeah? You're passing it on. What about a constant equals a variable? So if my constant was 10 equals 20, that would not be allowed because you can't change a constant. That's not allowed within the rules of the language. So not allowed, people, not allowed. So you've got to use your brain and be a bit logical. All right? So that's what semantic analysis does. Now remember, you can get errors. We talked about it before. If you don't stick to the rules, you will get a syntax error. And a syntax error, every single person that's watching right now, you have made a syntax error in your life. I haven't because I write perfect code all the time. I'm just like a robot. But you, syntax errors left, right, and center. Normally, your integrated development environment, Visual Studio Code, picks up on this. And it automatically puts a red line underneath it so you correct and sort your life out, which is fine. That's good. That's what we want. Live syntax checking. Saves us compiling and then figuring out we've got a problem later on. Okay? So only when it's 100% correct do we move on to the next stage. So lexical, syntax, semantic. After that, you've never seen me make one. You're a liar. I will call you out. Lies. Abstract syntax trees look like this. Here's a pretty picture that I draw or stole before. You can see that. What does that look like? What data structure does that look like? Question for the chat. What data structure does that look like? Anybody know? Ooh, question. What data structure does that look like? Kind of says it at the top. Oh, a binary tree. A binary tree, yes. Okay, binary tree. So, if I was let's talk about traversal. All right, which 3 types of traversal? Go. Tell me. What types of traversals do we have? There's 3 types. Oh, we're learning so much today. Doesn't it feel good? I hope you've all been revising. Oh, abbreviated. Very nice. MRIS. Oh, Ritz. Read your name wrong. I can't read. Left node right. Left right node. Node left right. Now that's great, but you're not telling me what they are, you big melon. In order. Thank you, Atta. That's one of them. In order. Any more? In order. Pre-order. Yeah. Pre-order. And post-order. Wow, I'm surprised my handwriting's that good with this silly thing. Right, in order. In order means in the middle. So node in the middle, left, right. Pre-order. Pre-order, pre-workout, pre-whatever, pre, start, right? So node, left, right. Post-order, left, right, node. Okay, now as long as you stick to whatever your compiler's doing, as long as you stick to the same traversal, then you'll be fine. So for this one, it took 2 first, then it went to the asterisk, then it went to the 7, then it went up to the plus, and then it went to the 3. So this one, if you don't know, was probably doing in order, I believe. Yeah, in order. So you go left first, so you got left node right, left node right, left node right. So you go left, you go left, you go left. You've gone left, there's nothing there. You take the node and write that down. Then you go to the right-hand side, there's nothing there. Okay, so you write down 2. So you've done all those, you come back up, you check the left branch, you've done that. You take the node next, so you take the asterisk. Wonderful. Yeah? And you get the point. Okay, if you've not done traversals in a while and you're struggling to work out how the hell I'm doing these pre-in order and post-order traversals, go and watch my YouTube video, like and subscribe. I don't get paid for this, by the way. Okay. After we've done that semantic stuff, we move on to machine code generation. Now, this is once a syntax tree has been generated, we will then convert the parts of the syntax tree into machine code. And we won't do it if there's any errors. Yeah, I lost my money. What is it? Monetization? Yeah, I lost my status because I stopped posting videos because I'm preparing all the new OCR videos like an absolute professional. I'm not about the money. I'm about the people. In order to do code generation, you have to perform 3 tasks. So the first one is to convert the elements of the syntax tree into machine code, allocate registers, fetch, decode, execute cycle, remember, and then optimize the machine code to improve efficiency. All right. Now, when you optimize machine code, when you're an old programmer in the early days, you had to make sure your code was efficient. Nowadays, we just slap code on the keyboard, chuck it in, hope for the best. That's because our compilers are going to do it for us. Oh yes. Most programmers nowadays, you write code very inefficiently because you're all rubbish. Higher the level we go up, so the higher level code, the more sloppy it's going to be. But we don't really care because we've got fancy graphics cards and loads of memory. Loads of memory. Okay? Your compiler will do optimizations for you. It'll edit code and it'll remove things, which is great. But one way to speed up the program is to limit the number of jumps that it has to do. So if you know anything about assembly language, you might know things about jump commands. Things like Let me write it on the screen. Where are we? Assembly language commands. Branch if positive. Yeah. Branch 0. You might have labels. Yeah. So labels in your assembly language. If you can limit those, you're going to be well better. Way better. Who's that? Bait me out. DCRE. What? Okay. Now, I've put these in because these haven't popped up for a while. And execution errors. So listen now to the types of errors you've got, because they'll be named differently depending on what the examiner does here. So you've got an execution error. I call it a runtime error. You might see it in the exam as a runtime error, but the formal term is execution error. If you think in your head runtime, these happen when the program is running. So that means it must have compiled and your program is running. All right? You'll be running your program like normal, and then all of a sudden, it'll crash out of the blue. Right? It appears to be nothing wrong. Sometimes it can be running out of memory. Sometimes it could be the instructions in the wrong order, or it reaches a piece of code that's a bit dodgy. But syntactically, the way it's written is perfectly fine. There's no red lines anywhere. It's compiled. Happy days. All right? There's some examples on your screen so you can talk about this in an exam. Division by 0. Programs hate that. Hate dividing by 0. Reading past the end of a file into the overflow or whatever. I don't know, Jake. That's your bandwidth. Dodgy. Stack Overflow. So you go outside the stack. Remember stacks, people? Do you remember those, what they look like? Stack Overflow. It's not the website I'm talking about here. Yeah. I'm talking about this is a stack. Here's some lines. We've got push. We've got pop. We got peek. Yeah. You got pointers. You push something on. You increase the pointer by 1. You insert it into this bit here, etc., etc. So you can go outside of that. Yes, good people. I like it. Philo. First in, last out. All right. You've got overflow the data type. So sometimes when I was testing students' coursework, I'd smash in the largest number possible to see if I could break your program. Because people just use integers. You can use like big integers or longs or whatever they're called nowadays. Or you're trying to access an out-of-range array element. All right? Cool. Now, translation errors. These happen before you've compiled. This is normally a syntax error. You're used to these because of your terrible programming skills. All right? Syntax errors are mistakes in the way the code is written, and translators can only execute a program if it's syntactically correct. Now, you'd hope in the syntax stage of the compilation process, your program would just throw an error out and stop. That's what normally happens. Spelling mistakes, yes, when people even try to copy things off the board or do whatever. I don't know what's wrong with you lot. You just miss random punctuation. Enjoy university, enjoy apprenticeships, degree apprenticeships, enjoy jobs, whatever. If you're not that accurate, you're gonna lose your job. Okay? Illegal variables. So illegal variables, basically that's where you try and assign something to a variable that hasn't even been created. Luckily for you, Python does that implicitly already. In normal languages, you have to actually declare the variable and declare the data type. God, help you lot when you have to get to that stage. So there's semantic errors and also linking errors. So you know that linking process I was talking about before? That's when your libraries haven't been put into your source code or your object code and it's now failed on you. Ha ha. Unlucky. Okay. Excellent. That's the end of that. Anyone got any questions? Oh, you know what? Let's tackle Big O. People are losing their minds over Big O here. I'm just waiting for questions. Any questions? Will you upload the gameplay? What gameplay? What are you on about? I think we are. Oh, Big O. You know what, right? I don't mind Big O, but I think the way the exam board describes it really does infuriate me, and apologies. Where is Big O? It should be in here somewhere. There it is, right in front of my eyes. Right in front of my eyes. Now, the reason why, Waleed, we have some faith, man. We have some faith. I'm happy to go to exam questions if people want it. If you want it, people, you shout for it. I will move to the exam questions if needed. In computer science, if you think about what big O is, all it does is it just basically says to me, as a computer scientist, this algorithm is efficient or not. That's it. It just says it's efficient or not. It's a categorization to show me how efficient something is. Now, if we have a look, there's all of the big O categories that you're going to get asked about. And what I've done for you is you can screenshot that. I'll give you the slides, but that is a beautiful summary. You are welcome. I spend my time doing this rubbish, right? That gives you the algorithms on the right-hand side to explain what complexity you've got on the left-hand side. Now, if you can identify what order the algorithm's in, then great, good on you. If you can't, but you recognise, oh, that's a bubble sort, then you could go, bubble sort. Bubble sort has 2 loops inside it. 2 loops must be order of n squared. Oh, damn. Right, look at that. Now, it gets a bit tricky where you get the logarithm ones. So, order of n log n, what that means is additional element. So, every time you add an element in, it increases the time or the space requirement slightly more than in proportion to the number of elements. So, it goes up a bit and a bit more. All right? When I talk about space and when I talk about time, time is when I put another element into my algorithm, another thing in my array, whatever. Time is how long it takes to process it. Right? So that's efficiency when it's running and doing its thing, like sorting or searching. When I talk about space, I'm talking about its memory usage. So when I add in a new element into my array, what does that do to the space requirement of the algorithm? Do I have to make another temporary variable somewhere? Does it exponentially grow in its memory requirements? Does it create a whole new copy of the data structure? You know, that kind of thing. That's what I mean by space and time. And you'll see some of the example algorithms on the right-hand side. It says space or time complexity. And that's really important because you've got to get that right on the end. So, for example, order of 1 or constant time, looking at the bottom bit here, right? These are our least complex algorithms. Get off. Go back. This is our least complex algorithms. And it says there, adding elements has no impact whatsoever on the time or the space required. So think about it. A bubble sort. So a bubble sort's space requirement, space, what does a bubble sort work on? A single array of elements, that is 1 times n number of elements, order of 1, right? It's one array, it's got n number of elements. Yeah, I can add on another element. Yes, I can add on another element, but you're still only going to need the space for one array. Doesn't matter how many elements you've got in that array, you've still got one array. It doesn't change. That's what we mean by space, okay? So that's there for you anyway. Let me just erase. I'll send the doc out later on. What are you doing? Get off, get off, get off. Right. Let's just go and have a go at one of these questions because I can hear Waleed whinging, moaning, complaining. All right. Okay. Skip on, skip on. Big O. Right. Here's a big O question. Read it first. I'll give you a minute. Just give it a read. Have a look at it. Let me know in the chat your confidence level out of 5 on this. 5 meaning you are super confident. I can do this, no problem. 5. 1? What on earth is that? Never seen it. Don't even know what's going on here. 0. Negatives. Whatever. Right? 0. Oh, we got a mix. Right, okay. 2.5. Half. Okay, good. All right, well, fair enough. It's good to be honest. Now, it says the algorithm conducts a basic statistical analysis on a one-dimensional array, right? One dimension. Remember what I said before about the bubble sort? One dimension, right? So I've got one array right here. There we go, one array, producing the maximum value, the minimum value, the sum, the mean, the number of values, and the range. The array has been populated with floating point numbers. So those people that have said to me 0 for this question don't even know how to go about it. Let me show you that you can get some marks. If all of them is off the table, let me show you how you can get some marks, right? It says the first question, evaluate the efficiency of the search algorithm and using big O notation, determine the growth rate for time performance. It's 5 marks this. Let me see if I can get you some of them at least. All right. Now, the first thing that we do is we need to think about the operations, the things that are going to affect the time or processing of the algorithm. All right. So let me talk about operations for a second. Operations. Okay. Now, what is an operation? And how do we count them? Now, sometimes, if you look back in the questions that I've put on in the past, some of the questions say, look at the addition and multiplication operations. An operation is anything that will cause extra processing. So you can think of it like, all right, what about an asterisk, for example? A negative sign, a plus sign, a division or something like that. What about an exponent, okay, or to the power of something? If statements could also count, else ifs can count. What about things like next I, for example? Next I will count because next I is basically I equals I plus 1, which is an addition operation. So you've got to think about what is going to affect the code and will it affect the time? So let's do this one, right? The first thing I would do is think about it like this. Here, that is a loop. Yes, a loop. So let's just ignore that for a second. Let's look at this set of code here and this set of code here. How many operations have I got going on inside there? How many operations? Now, if you think about it, these are all variables that are being declared, right? Variables. And this is all to do with memory, right? It is not to do with time performance. It is space. Space is memory. So I'm ignoring all of those declarations. These ones here, I am assigning 0, 0 into total. This will require processing, and therefore I've got data going in there. I've got an array at position 0 going into max. I've got min, array position 0, and I've got I being set to 1. So there, I've got 4 operations going on there. Okay, 4 operations. As I move down to the bottom part of the code, what does output mean? Right? Output is your algorithm showing something to the screen, processing the data, concatenating it here, and spitting out the variable there. So you've got a string concatenated with a variable. This here, in this exam board, counts as operations. 1, 2, 3, 4, 5, 6. Now, if you look at this, you've got a division in there. You've got a subtraction. You don't have to count those twice, right? You just count the whole line. If you see an output or you see something like this, you're going to write it down. So 6 there in total. So that gives me 10. Yeah, 4 plus 6, that is 10 operations. I think I just answered your question, Jake. I think. All right. So you've got this whole line being 1, even if it's got a comma, or it's got some kind of operation, a division operation in there. Okay, 10 operations first. Now we do the same thing, but inside the loop now, right? Inside the loop. Now this loop, how many times is it going to actually iterate? How many times is it going to loop? Well, it's going to do this code while I is less than n. I is less than n. Does anyone know what n is? Can anyone tell me what n is? Anyone got any ideas? Well, I have no clue what n is at the moment. Not a clue. So I will say this loop will operate or will iterate n times. Right? It will operate n times. And if you've seen Big O before, you might have looked at if statements that have got n running, another if statement inside it in there, and you've got a loop there. Like that. And that'll be n. You've got if statements, and you can have a loop inside here again. Right? And that will just be n as well. N by n is n squared. If you don't know how to do that, or you've not seen that before, please go back and watch some of my Boolean Algebra, my Big O notation videos, and because I show most of the exam questions have nested loops inside them. If I have a loop within a loop within a loop, and they were all n, n, and n, how many times is this code going to operate? What order is that going to be in? Does anybody know? So that's n, n by n, n by n by n. It's n to the power of 3, isn't it? It's n cubed. All right? So that's something to point out, because usually they've got nested loops in to try and force you to do that. So I'm here now in this do while loop, and it's running n number of times. So whatever line of code is going to go on in here, it's going to run n number of times. We don't know what n is. So what counts as an operation in here, I hear you ask? Well, firstly, your if statement will count, because you've got to compare. A comparison will require processing. Your else if, or your else, for example, will require some processing. So that's 1 there, 2 there. Now, be mindful, okay? Don't worry about the lines inside here, because if you look at them, this is assignment, isn't it? But you've already got the processing for the if block there. Okay, so you don't need to take the line inside, and you don't need to take the line inside that either. They're already covered by the block itself. This one here, would you say this is going to be 1? Anybody want to take a guess? Do you reckon we're taking that one? Set total equal total plus array. Well, yeah. Okay, good, yeah. Because we've got a plus in there, and also we've got a plus in there. So there's 3 there and 4 there. All right? Now this is 4 operations that are being executed n number of times. So that, I would say, the I loop runs n times. There are 4 operations inside the I loop. And that is 4n. Okay? So once you've worked out your number of operations outside the loops and inside the loops, tell us the number of operations it's going to run, tell us how many times it's going to run, and then add them all together. So that's 10 operations plus 4n. Okay, 10 operations plus 4n. Now, what I will say to you is if you actually spotted that it was 10 operations, you'll get 1 mark for that. if you told me that the I loop runs n number of times, you'll get a mark for that. If you told me that there was 4 operations inside the I loop, you would get 1 mark for that as well. If you added them together, you would also get a mark for that. All right? So well done you. So those people that said to me before, the 0, okay, if I gave you the rules there to figure out operations, I'm wondering if you could you add up the operations if you knew what the operations were? Now you do. Now you know an operation is anything that will cause processing. Could you add them up? Maybe. What about, could you identify the loop or loops? How many loops there were? If you could, and you've worked out how many times they're going to loop round, then you could tell me how many n the loops are going to go. Is it just one loop, n? Is it a loop inside a loop? That's n squared. Is it a loop inside a loop inside a loop? That's n cubed. Okay? Could you do that? Could you get at least 1 mark? I don't know. You've got to ask yourself those questions. At the end of this, to get our last mark here, we've got to say, as we add data in, so as I increase n, let's say n was 10, or 20, or 1,000, what's going to happen to this algorithm? Well, when n is 10, it's going to be 4n. So n's 10, right? So you're going to do that. And then you're going to go 20 and 1,000. So as I increase, let me just get rid of that. As I increase n, the major impact it's going to have is going to be on the 4n side of things. You notice how 10 never changes? Does anyone know what we call 10 in our final equations? Does anyone know what we call 10? What is it? It's not just 10, it has a name. Things that don't change. What do we call them? A constant. Very good, thank you. So as we scale up and add data in, 10 becomes irrelevant. As we add data in, 4 stays the same. It's irrelevant. As we add data in, n changes. N has the most change happening to it, and therefore this algorithm is order of n. Okay? And what I would do when I'm writing my final answer, I would say that as data increases, or as n scales, n becomes more dominant. And I would use that word dominant, because that's what big O looks for, the most dominant part of your equation. All right? So there's your mark for determining for n. Oh my goodness, look at all that writing. Now, apologies for going through it slowly there, big people, but I feel like it's quite important. Some people do get it, some people don't. Some people feel confident, some people don't. If you look at how many times it comes up over the years, my goodness, this is highly, highly likely to come up, this stuff. Okay? Okay. Now, what I need you to do is I need you to look at the next question, because what's different about the first and second question is the fact that it's talking about memory space. Memory space. All right? Just try to get rid of all this rubbish. Memory space. So, oh, look at that. Is set I equals I plus 1 classed as one operation? Because I'm thinking set I is one operation, I plus 1 is another. You're talking in this. So I equals I plus 1 is definitely one operation. The equals part is not one operation. The plus, no, it's all classed as one. It's just one operation. That I equals I plus 1 is one operation. So once it's on that line there, if you see that and that, even though they're separate operations, the processing occurs in the block. So that's one overall. That's all. Hope that helps. Right, second part of the question. determine the rate of memory spaced. Memory space during a single run. That's one run of the algorithm. One run of the algorithm. Now, what happens here, people, is we don't need to look at the algorithm. For these memory space questions, you need to look at what's inside the question. What's inside the question? Can anyone tell me what data structure we're going to use? Anybody tell me? Right, we've got an answer in there. Order of 1, we said. We're using an array. Thank you, Toffa Joel. So we're using a single array. It says there on A, so a single one-dimensional array. So 1 times a single dimensional array. And we can say here that the algorithm only uses one data structure, which is a one-dimensional array, and therefore the total storage requirement is 1, which makes it order of 1. Pretty simple, pretty straightforward. Just look at the question, people. Look at the data structure it's asking for. That's it. It's one array. It's order of 1. That's it. Bit further down though, what about that one? Identify the type of time complexity and draw a graph of the algorithm above to illustrate the order of time performance. Well, you know what? Why is this worth 4 marks? That's the question you've got to ask yourself. And I make no apologies for saying this again, because I said this to my class loads of times. I made them do it first, and they all basically got 1 or 2 marks. I think one person got all 4 marks for this kind of question in my classes. So basically, I'm going to draw my graph. Right? You'll have no graph paper. If you've got a ruler, good on you. Now it says there, time complexity. What was the time complexity before? It was order of n, wasn't it? Order of n. Right? Order of n. Now what that means is, as data is put in, so does the time. In equal proportion, so does the time. Oh no, I tried to draw it slowly and straight. Order of n looks like that. It is a linear complexity. Thank you, Mr. Wong. Linear complexity. And with that, you will get yourself a grand total of 1 mark. Can anyone tell me? Can anyone tell me why I've not got 4 marks? Anyone know? Because the system's rigged. Nope. Labels missing. Thank you very much. My goodness, if you forget the labels, I don't know what I'll do. I was going to say I'll throw you out the window, but I can't do that. It was bad, but you know what I mean. Right, firstly, right, this is linear complexity. Now, oh no. Right. Saying linear complexity will get you 1 mark. On the left-hand side, if you said time to complete, because it's time, and then at the bottom, you said size of data. Yeah? 1, 2, 3 marks, 4 marks. The way I remember this is big O notation deals in space and time complexity. Space and time, right? So time, if it asks you about time, that goes there. And as the data increases, or you put more data in, what happens to the time? So it's size versus the time there. Elements works. Yeah, elements works instead of size. Yeah, elements of data or elements themselves, that'll work. I'll accept that. That is fine. So that's big O notation there, people. I don't know if that helped or not. Do go back and review my big O notation slides, because there's little cheats, hints, things like that in there. They're very useful. And if you can't find them, email me. I'll send them to you. Okay. Another thing that pops up all the time. I don't know how. Waleed, are you still there? Well, yeah, he is. Right, good. What we're going to do is something that pops up again. Where is it? No one asked for it. Is everyone confident with Bacchus no form? I want to have a go at this Bacchus no form question that I picked specifically. Skip past that. Right. See that there? See that? Bacchus no form pops up quite a lot. Does anyone know any of the rules of Bacchus no form? Bacchus no form rules. Now, the reason why I picked this question is because it has a syntax diagram with it, and we haven't got much experience with syntax diagrams, or I don't feel like we have. Yeah, BNF is light work. Good. Just give me a confidence rating out of 5. How you feel on Bacchus no form? 5 being I can do Bacchus no form, or 0, I am not good at this. Four, yeah. 4 out of 5, 5, 3, 4. Okay, we're pretty confident-ish. It's the diagram I have no confidence in. 3 out of 5, yes. Can't you make the side? Can't read it. Can you make it? I can't make it bigger. What is this? Need a bigger screen. Wait, watching it on the phone. What is this? I need space to write. For Monday, yeah, right. What you can do is you can find the 2023 paper and have a look at it. I think it was one of the questions in there, if I'm not mistaken. What I will do is, using my amazing technology, what about, let's find it. It was in here. There it is. It was the one from last year. Let me zoom in for you. Let's scale it up. Right. I'll go back to my normal screen in a second, but let's just have a look at what it does. You see that now? No, mate, it should be on Google Sites. Manufacturers use European article numbers, EAN-13 standard for barcoding products. Each EAN-13 barcode comprises of a country code, manufacturer's code, a product's code, and a check digit. All EAN-13 barcodes are 13 digits long, separated by hyphens. Country codes are within the range of 000 to 999. Manufacturer's codes are 1 to 5 digits, and product codes have a varying number of digits depending on the size of the manufacturer's code. A check digit, which could be either 1 or 3. There's an example. So you always get an example back as no form. 500-123-123-456-1. That's an example of a valid EAN13 barcode. So it wants us to produce a Bacchus no form definition for the EAN13 barcode. So I'm going to switch back over now to my primary screen. Look at that. Oh man, I'm really moving up here. I don't know who Blob Blob is, sorry. Yeah. I will shadow ban them in a minute. Blob Blob. Okay. Need a pen? Where's my pen? Okay, let's do this one. So, what we're going to need first is we need to think about it in regards to country. So the first one, let's have a look at our country code. Now, what students do is they do something really stupid. What they'll do is they'll say, oh, you need a recursive digit here. No, you do not, people. So if I write on the right-hand side, I'll try and do it next to it, actually. But chevron first, we declare a rule called digit. Colon, 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 colon equals, right? If you do this wrong, you will lose a mark for syntax. So don't do it wrong. Now what you can do is you probably could do digit, digit, digit if you wanted to, or you can basically do 0, oh my goodness, 0, 0, 0, 0, 0, 1, dot, 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 and then have 0, not 0, 9, 9, 8, 9, 9, 9. Okay, something like that. You're showing the examiner that you're fine. You can do that. You know what you're doing. You're not going to be there all day writing, but what you do need to do is make sure that you've actually got your chevrons, your colons, and your equal symbol correct. After you've done that, you need to make the manufacturer's code, which are between 1 and 5 digits, okay? So if I put down here and I called it man for manufacturer, what you're going to need is you're going to need some kind of digit to do that. I probably should rename this. That's not a great name for it. Let me just get rid of that for a second. Sorry, I can't see the chat for a second. I'm erasing things. I'm going to call it something else because I'm probably going to name it after the country code. So I'll just put country here. Okay. That'll leave me then to create my digit rule, which is just a normal digit rule. There's one of these in every question. So if those people are not confident, all you have to do is be able to create digit rules. Can anyone tell me what the common student error is when declaring a digit? Anybody know? What's the common error that students make? Nobody knows? Yeah, missing 0. Exactly, Tuffagill. At least you listen, Tuffagill. You turn up late to all my lessons, but you do actually listen sometimes when you're there anyway. Yeah. Okay, so country codes, manufacturers between 1 and 5 digits. So I've declared a digit rule there, and then I'll say manufacturer can be 1 to 5. So they can have 1 digit, or they can have 2 digits. Oh, this is going to take forever. Digit. I'm going to get arthritis doing this. And then you go digit times 3. Do you get the point? Do you get the point? You'd write them out, people, right? I'm not going to do all of them because we'll be here all week. Digit times 4. Yeah, you'd have to write it out in the exam. Apologies, but you just got to do it, right? Up to 5. Okay? Then, after that, you've done the manufacturer's code. So I've checked that one, I've checked that one. Product codes have a varying number of digits. Now, what does varying number of digits mean? Does anybody know what I need for varying number of digits? Any ideas out there? Put it in the chat. Varying number of digits. Okay. I'm going to answer Mr. Wong's question. Good, thank you, Tuffagill. Again, look at that, it's quick. So, Mr. Wong, you can't use recursion because it says between 1 and 5. If I use recursion, I could have anywhere between 1 and a billion, right? So that doesn't fit the rule. So you can't use recursion if it's exact, like 1 and 5, okay? However, this is a varying number depending on the size of the manufacturer's code. So what I need to do is I need to create my product code, which will be, let's call it digits here. And now you'll get a mark for this even if it's incorrect. So attempted recursion gets you a mark. So digit, so you must have at least 1 digit, and then you can call digit again, and then you would recursively. This is my recursive call here, people. I'm writing my recursive call, which is called digits with an S. That will take you back and start you again. That is recursive, people. You cannot leave it as times 4. No. You'd have to do times 5. But you can't write times in you've got to write them all out individually. So digit 5 times. I'm not doing it. I'm not got enough time. Okay? After you've done that, I'm just going to say product code. So let me write product or prod dot equals digits. There we go, product code. And then I've got a check digits, which is 1 or 3. Now be careful, people, of stuff like this. 1 or 3. They think you're an idiot and they'll think you'll do 1 to 3. All right? So I need to write in here, I'd write check equals 1 or 3. These are terminals, these are non-terminals. Okay, I've done all the rules now, I think. I just need to assemble the thing. So I'll write here, because we're going to do a diagram, barcode. So barcode, colon, colon, equal symbol. And what do I need for this? So I need country code. So I called that country. That's me 00 to 999. Excellent. Then after that, I'm going to need a... Now, if you look there, I nearly forgot then, but I'm obviously a star student, so I'll put my hyphen in there. Now, can anyone tell me why hyphens don't need to be in a rule? Anyone tell me why hyphens don't need to be in a rule? Thank you. You can let me know in the chat while I write the rest of this out. Country, man. What else have I got? I need my product numbers. Product. Prod hyphen. Check. Hyphen does nothing. No, it's just not needed. No, it's only one character. Well, no, not the right answer. They never change. No. Useful for organising. No. Oh, people. Ho, ho, ho. Ah, looks like I've got you all. Not concatenated. No. It's something to... No, I'll just tell you. It's... Oh, Ritz. Oh. Ho, ho. It's a terminal, people. It's a terminal. Digits, symbols, characters, they're terminals. If it's terminal, yeah, if you've got a terminal illness, it means you've come to the end, isn't it? So it's the end. There's no more, right? So you can't interpret anymore. So therefore, this, if you've got terminals, you can put terminals straight in the final production rules. Okay? Bear that in mind. So you can write them directly in. Like you might have seen in some examples, the Backus note form, you might just stick on the end at osfc.ac.uk. Now you can put that directly on the end of a production rule because all it is a bunch of terminals. All right, that's it. Happy days. Oh yeah, let's ban someone. Who are we banning? Oh, he's threatening people. Oh. Yeah, let's do that. Should we ban him forever? There you go. Oh, there we go. There you go. There you go. Yeah. Time out. Yeah, justice. Swift. Right, the second part of the question is the one that people struggle with the most. Now, if you're thinking about, this is 9 marks, this, people. Imagine that, 9% of your exam on this question. So let's produce a syntax diagram to define a barcode. So what that means is, that means you need to give me a single diagram for your final production rule. Wow. That is awful. Right, okay. So what's my final production rule? It's barcode, isn't it? So what does barcode consist of? Well, a box there, and it'll have country, which is my 00 to 999. Then it's an arrow with a line. So remember, this is non-terminal. That boxes are non-terminals. Then a circle or an oval with a hyphen in it, because that's this bit. So tick that off. Hyphen, tick that off. Next is man for me. So there's another line. Because again, look, this is a rule. So there you go. No, non-terminal rule. Man. Oh my goodness. Oh. Uh-oh. Malfunction. Try again. Let's try that. Right, man. After that, we've got another hyphen. Arrow. prod. Now, what can we say about production here, people? This is where you need to really pay attention, because this kind of stuff here is where you lose a mark for this kind of stuff. If I put prod there, then I would lose a mark. What is the production rule? It has a special, what do I say? Special responsibility? Special, I don't know what the word is. But it has some features, some special features. So we know it's recursive. So we know we're going to have to loop it round. But what you're doing is you're not looping the production rule itself, called products there. What we're doing is we are looping our digits. So I would replace this here. I put my pen there. I would write digit. And the rule is called digits. So I put digits in there. This is my recursive rule. Digits is my recursive rule, people. Look, digits, this one. This is the recursive bit here. So you've only put the name of the thing that's recursive, and to draw the loop round there like that, you put the arrow. All right? Then you've got a hyphen. And what a lot of people will do is they'll put the check digit or the check box in there, like so. You'd say check. Or some people would say hyphen, arrow for 1 and another arrow for 3. That is also allowed, but I would just do this because it's way easier, right? It's way easier. Okay? That is 4 marks there, people. You get 1 mark for country and manufacturer code boxes. So for those 2 together, right? 1 mark for that. You get 1 mark for the terminal symbols. So that's those, or the checkbox. You get 1 mark for the hyphens. So all the hyphens together. 1 mark for that. And then you get 1 mark for the repeating part, so the recursion, the box there that goes back. But you must have the arrow. Must have the arrow. Hello, Jack. Any questions? I'm fielding questions now, people. Any questions? No. If you can, I hope Backus no form comes up. It's usually where our students do quite well. So I'm hoping and praying. Good. Can you do the instead of hyphen? No. You can't do that because that line there is a pipe. How come digit, no S, wasn't needed? Because digit there is the actual number, but the recursive rule that I want to repeat, is called digits. Digits. I think Jake's talking about using hyphens. Right there. Okay. Head back to the start. Right. This is now, we're going to have a 4-minute break. 4-minute break, and then I'm going to come back, and then you can, I'll do shout outs. Whatever people decide that they want to do, I will do. What is the small diagram? Okay, people, you can go off for your 4-minute break. Amber Singh. Well done, you. Shout out completed. Why are people asking for shout outs? What are you doing? What's wrong with you? The red stuff, okay, blob. The red stuff is component 2. This is what people asked for me to cover, and the red stuff is component 2. Oh my God, Ahmed, you are crazy about this document, aren't you? Can you do a big old question, but with space complexity? There never is space complexity. what you saw there is the same format for all other backwards no form questions. You can have a look at my other videos if you want to as well. That's fine. If you're, are you from my college, Ahmed? Are you from my college? Never. Let's go back here for Waleed. If you're not from my college, you just let me know, and you have to send it to my email. Jack, you know what? I've never even seen you. I don't think. You might have heard of me, but I don't think I've ever seen you. Mr. Wong, can there only be one operation for each line of code? One operation? Oh yes, yeah, in big O notation, yes. Okay, Ahmed, you need to send your send me an email on jbr at osfc.ac.uk, and I'll send it through. Okay. We're just going to have a short interval and we'll be back shortly. What you can do while I'm gone is just stick what topics you want to do in the chat, and I'll be sure to cover them. And we're back. Oh yes. Question time. What have we got? Jack's having a crisis of some kind. Wonderful. Can you say what? That's fine. Object-oriented programming. That is a great shout. Object-oriented programming comes under programming paradigms. I'll talk about that in a second. Separate chaining questions, they don't come up. Yep, Namir, no problem. Send us an email. I will send 2023 out to you, no problem. No problem. Network topography, and I don't know what it is. Okay, be careful with topographies because this example doesn't actually do topography. Doesn't actually do topography. What you can do is, we'll go through programming paradigms for in just a second. Can people tell me the different types of paradigm we have? What different types of paradigms do we have? What do we think? Yep, event driven, good. Procedural, excellent, yeah. Not declarative, no. Object-oriented, yeah. Markup, perfect. Markup languages, such as HTML, XML. Visual languages, yeah, such as Scratch, stuff like that. Procedural, Python's a procedural, but it's also event-driven, depending on how you use it. Non-procedural ones, I mentioned them right at the start of the live stream. They are things like AI, grammar checking, language models, that kind of stuff. Visual, talked about that, yeah. Object-oriented, markup and visual. Object-oriented, if you didn't know anything about it, here we go. Now, the one in my head, the one that I learned was Java. Java is an object-oriented programming language, or modeled that way. But basically, most modern programming projects use object-oriented. If you go to university, the chances are you'll do procedural as like an ease into programming, and then you'll move up to object-oriented programming. So once you understand the basics of procedural, that's where you go. So it models real-world environments normally, and it's short for OOP. That's how we say it. So with that, you also get everything that a procedural language normally gets, such as selection, so if statements, iteration, such as looping, assignments, just like assigning things to variables, identifiers and constants as well. But the key difference is here that you have three of these words here are really important: classes, objects, and methods. Classes, objects, and methods. Now, if you did the first year exam, what you would have done is you would have seen a box on a class diagram like this. All right? And you'll have like pluses and minuses and hash symbols and all sorts of stuff and words in here, and you'd have positive something text and then a something with brackets on and stuff like that. This is our object-oriented class diagram. So a class is broken into two parts. You've got attributes, and there are variables, and you've got methods, which are our procedures or our functions. All right? Now, when you have a class, think of it like the template for everything. It is the blueprint. It's the master copy of everything that we use, and we create little copies of it, and they're called objects. Now, when you create an object from a class, that's called instantiation. It's a fancy word for saying it's just born, it's just created from something else. All right? So classes, objects, and methods. Classes and procedures both offer something called modularity of code. You know when you take all your code and you break it into small pieces? Yeah? Modularity. The more modular your code is, the easier it is to test, the easier it is to manage and manipulate, and also integrate into other parts. But classes allow the developer to produce more reusable code and relate their design more closely to reality. So these are the characteristics that define object-oriented languages. So you might see these words as well: encapsulation, polymorphism, inheritance, classes, and objects. Okay, you'll see those in as well as abstraction. All right. Now those are not to be. Don't be scared by them. You will not get asked about all of them. I saw a question the other day that basically said, explain the use of encapsulation and inheritance or something in object-oriented language. So it's like a 4-marker, I think it was. Just wanted you to describe what these things do. And I've put a very, very brief description on them here. But for me, this is the most important thing. If you can get your head around a class, an object, and a method, you are well on your way to understanding this. So I put it in this term for you. When you're doing object-oriented languages and you've got classes, think of a class like a car. Your car, my car, family's car, that kind of stuff. A car has very common properties. All cars, as far as I know, have wheels, right? Might differ in the amount it's got. Might have 3 wheels, might have 4 wheels. They all have doors, as far as I know. They all have a bonnet. They all have an engine. They all have a fuel tank. They all have seats. They all have steering wheels, that kind of stuff. Okay? With those, you need to then consider, all right, well, if I'm programming it and I'm creating variables such as steering wheel, seats, engine size, fuel tank, etc. If I'm doing that for your car and then I'm going to program my car and I'm going to program someone else's car and someone else's car and someone else's car and someone else's car and someone else's car, it's going to get boring pretty quick. It's just a waste of time. So what we do is instead of that, we declare one class called car. That's got all the properties in that every car has. And then your car can be created from that. So you've got an Aston Martin. So you create an Aston Martin, which is a type of car. A Jaguar is a type of car. And Ford is a type of car. The thing is, with my Ford that I used to own, it had heated windscreens. It had self-parking. Now all that is distinct to Ford. Jaguars didn't have them, Aston Martins didn't have them. But it had all the other properties. So you share the main properties, the blueprint properties from the car class, and then you customize it with your extras on top of that. So Ford, Jaguar and Aston Martin are all children of the car class. Right? They're all born from it, they're all created from it. Just like you, your brothers and your sisters, yeah, you all came from your mother. Right? So your mother would be the class and you would be the objects from that. Okay? Now that's how classes work. So if you think about it, class has 2 main sections, the attributes and the methods. And those are those things I was talking about before. You will not be expected to draw a class diagram. I've never seen it. It happens at AS but not at A2 or second year. So you've got your attributes and you've got your methods. So these are your variables and these are your functions or procedures. Okay? Methods are fundamental to object-oriented languages. A method is a piece of code that implements one of its behaviors of a class. So for example, if this is a Tesla, it's got turn left or turn right, for example. It also has go and it has stop. They're all methods as well. So in order to identify an individual car, it must be described, and in object-oriented languages, it means creating an object. So we instantiate or create an object from the class. So to set an attribute from the class, you need to use the reference created during instantiation. So what I'm saying here is Ford. So here's my big car class. Car. Normally, in languages, a capital C like that will tell me that it's a class. So I'm saying create a new car and we're going to pass the properties of that to Ford. And what you'll do is you'll get a Ford pop up like this and it'll have all the properties inherited from car. So they all pass down to Ford. And then, once I've instantiated it, all I've got to do is I've got to use the word Ford. And if I put a full stop, you will get access to all of the variables or the attributes from car. So in here, it must have had reg number. Must have had that in there. It must have had make. It must have had model. And when I create a Ford, it gets a copy of model, a copy of the make, a copy of reg number, and then I'm saying change it to YR99. Change it to Ford. Change it to Fiesta. So you can change it just for Ford. If I wanted to create a new one, all I would do is I would say jag equals new capital C car bracket bracket, and what that would do is that would create a new instantiation of the new object, and it would say Jag inside there, and it would have all the same properties such as reg number, make, and model would go in there. And that's why it saves so much time. That's why it's so efficient, because you're just using the car to create that for you. All right. So that's what I said there. Attributes are created as variables within the objects and are accessed by using a full stop between the object and the name and the variable. So with that there, you can assign attributes or use them in other expressions. And I said before, didn't I? If I've got my Ford there, what if my Ford's got a custom, a custom thing that it can do? Well, I might in here, locally, I might declare windscreen. Yeah, it has a heated windscreen. So I declare that locally. But car doesn't have to get a new property called windscreen, only Ford, because it's local just to the Ford. So you can mix and match and add your own in as we go. So that's object-oriented programming there. Now, if you think about these terms for a second, when you create your objects and your classes, you can get encapsulation as well. So if I show you a diagram here, encapsulation is just what we call a technical implementation. So the thing inside it is hidden within the object. Now, the only way I remembered this when I first learned it was talking about capsules. You know, like a cold and flu pill, right? They come in these little dissolvable capsules that are usually red and white or something. And inside of it, it's got the actual thing that it's got caffeine and whatever inside it to help you feel a little bit better or whatever, or paracetamol, things like that. So encapsulation, it has capsule in it. So when I think about capsules, the payload or the thing that helps you out with when you've got a cold or a flu is hidden inside the capsule. And that's how I remember encapsulation. It's the method of hiding the implementation of a class. So you get that horrible paracetamol or whatever, powder, but you can't taste it because you've had the capsule, which basically is hiding the implementation or hiding the paracetamol for you. And it's the same thing in object-oriented. It can stop people getting access to certain things and messing them up. And that's why we use encapsulation. So classes can hide how they work from developers who may wish to use them in their programs, because you don't want developers messing with certain parts of code. Anyone using the class needs only to understand the interface of the class, so its methods and attributes. They don't need to be changing any of the code parts. So I don't know if you can see that because it's quite small, but inside my car there are things that I don't want people to change, so I will hide them, such as the acceleration. It's limited. My car's limited to a certain speed. I don't want people to change that. The gear you can definitely change gear, but you can't go more than 5 gears or 6 gears depending on your car, so that will be limited as well. And also brake. There's a certain type, so when you brake, you can't brake too hard because you'll come out the front window. So you have ABS where your wheels move slightly. All right. So there's certain things that you might not want them to change. You might want them to change. The brand, the speed, the top gear, and the colour you can't change, but others you might be able to. Encapsulation talking, yes. So for those people that did AS last year, if you think about it, you've got a public method, which everyone has access to. You've got a private method, which only people inside the class have access to. And you've got protected there. Oh my goodness, it's not writing. Okay, public, private, and protected. Okay. When you see those, they're just symbols to say whether someone can access or not. Now with inheritance, if encapsulation is the method of hiding from certain people, inheritance is dead simple. So I'll skim over it really quickly. It's just like when you inherit genetics from your parents. The class itself, whenever you've got a main class like a car, you might have a Ford is a type of car, and then you might have a B-Max, which is a type of Ford. You might have C-Max, which is a type of Ford. You might have a Mondeo, a Titanium. Oh, look at me and my Ford knowledge. you can have children of the forward class. We call this top one the parent. Okay, and these are all children. You might see them referred to as the superclass, and these are all called subclasses underneath. So inheritance is when you inherit from something else. So there's an example of inheriting. Instead of having a car and a van and declaring everything twice, you just have road vehicles, and accelerate, brake, current gear, gear up and gear down is all passed into car, and these are also passed into van. Reusable code. That's what we want. Now, polymorphism, I've never seen an exam question on it, I don't think. But basically, if I said to you A plus B, and A is 10 and B is 10, what would the outcome be? Hopefully, you'd say to me, it's going to be 20, John. All right? But if I said to you, what if A was cat and what if B was dog? And you added them together. Anyone know what that would get? Cat plus dog? Anyone know what that equals? Does anybody know? Cat dog, yes. So the system, the code that you're writing, or the object-oriented paradigm will detect what the data type is. So if this was an integer and this was an integer, it's going to perform an arithmetic operation or arithmetic operation. Okay? If it detected this was a string and this is a string, it's going to perform concatenation. So how does the system know what you want to do? Well, that is poly, many, morphism is form. So it can change its behavior. Polymorphism is the changing of behavior. Okay? Then you can override behaviors. So you can force it to do what you want to do by saying, well, A is going to be of an integer type, and therefore I'm going to cast it to that, and B is going to be of type float, for example, and I'll cast it to a float, add them together. So I'm going to override the behavior, and that's how polymorphism works. Abstraction, there you'll see the Manchester Metro, and with abstraction, the beauty of it is you don't need to know what's happening. All you need to know is that it's going to do what you expect it to do. So when I drive to work in the morning, I don't know how that engine works. I don't know all the complexities of how it's all built. But I know if I put my key in the ignition and I turn it and I press the clutch down and I put it in first gear, the engine will fire on and I can basically drive off. Right? All that difficulty and all that complexity is all removed. Nice and easy. Job done. And that's the same. If you look at that map down there of the metro, you can't see any of the road network, you can't see any of the canal network, you can't see any of the cycle network, you can't see all the buildings, you don't know what it passes through, etc. You just see straight lines, which they're definitely not straight lines. The metro is nothing like that. Yeah, but it's made simple for you. That's abstraction, making life easier for you. And object-oriented programming is fantastic for abstraction. Okay, back to the start. What do we want next, people? Let's have a look. Let's have a look. Requests, shout them out. The pseudocode, well, I don't know what the pseudocode is going to be. I can tell you what was on previous papers. So the 2023 paper, we had an insertion sort, didn't we? Binary search came up 3 years ago. A linear search hasn't come up. So, if it's a linear search, we are laughing. We are laughing. Data structures. Quick sort. It's hard to say with quick sort because it has come up in the past, but it was a while back. Let's look at data structures. Do you know all those ones? Do you know all those data structures? Hash tables probably is the weakest one, I imagine, for the groups. I don't teach data structures. I didn't this year, anyway. Arrays, 1, 2, and 3 dimensions. Records. So what's a record? It's multiple data types under one identifier. A stack. No separate chaining. Nope. Stacks, queues. Stacks and queues will come up usually together, although you just got to know the methods and also how to pseudocode a push and a pop method. Yes, or an enqueue and a dequeue method. You got binary trees, so that's traversals in there. You got linked lists, you need to be able to add and remove from a linked list, and you've got hash tables in there as well. Usually it's just descriptions for hash tables. So data structures come in two types. You've got static, they don't change, and you've got dynamic as well. If you've looked into Python before, you might have looked at their data structures and gone, what on earth is Python doing? They've got something called a tuple. A tuple doesn't expand or contract, and you can't change it. It's immutable. You can't edit it. But data structures are static or dynamic. Now, when it comes to one-dimensional arrays, these are the simplest of all data structures. So you've got to remember 3 different parts to an array. It's just a collection of variables of the same data type. Do not compare, do not start writing about a list. A list is nothing to do with your exam paper. A list is Python specific. It's a programming thing, right? Arrays are what you will need to talk about. Okay, same data type. So one data type under one identifier. Each variable or element in the array has an index position. Okay, so to draw that, actually just put that there for a second. Just remember that when you have an array, one axis, lots of elements, who knows how many, 0 index based, goes up to whatever. Okay, all of one data type. So if this is 4, that's going to be 6, 9, 11, 57, 1. Right? If it's integers, it's all integers. It has a name, such as the worst name ever, my array. So elements, index, positions, identifier, 3 parts to an array. 2-dimensional arrays. Think about 2-dimensional arrays as X and Y axis, rows and columns. Okay? So this code shows how to declare a 2-dimensional array. You've got names, and if you think about it, Sam, Lucy, James, Jack, and Jane, they are in one row. Peter, Sarah, Adam, Karen, and Verity in another one. Emily, Edward, Dominic, Justin, and Jake. Right? Think about it. 1 row, 2 row, 3 row. The brackets are what usually throws students off. Okay? One set of brackets is going to be, in a 2-dimensional array, it's going to be 1 row. If you have another one, square brackets, 2 rows and 3 rows, like so. All of them get wrapped in square brackets. Happy days. Then, 3-dimensional arrays. Look at the brackets again. You've got doubled up on the brackets. So you've got Sally and 70U, comma separated in one set of square brackets. Then you've got Bert and 7AB in one set of square brackets, and both of these two are wrapped in this one here and this one here. Martin and Susan are wrapped in their own brackets, 1 and 2. 1 and 2. So if you look at that, what it looks like in the three-dimensional array, think of it like it's groups, or groups of data, groups of two-dimensional arrays. So we know that this here is our x and our y coordinates. Yeah, our two-dimensional array, so 2D in here, 2D in here, and they're all wrapped by name and tutor group as a three-dimensional array. Never seen a question about a three-dimensional array, actually. Usually they stick to 2. Right? Usually they stick to 2. Records. The good thing about records is you've got multiple data types. So you've got all of your different fields. These are called fields, by the way. They are all under one data type. So that might be my record. And what you can do, if you can combine these as well. So you've got an array. Inside your array, you've got a single record with all your stuff in. Then you've got another one in here with all your stuff in. You've got a third element, a fourth element with all your stuff in there. Blah, 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 blah. All right, multiple data types. Stacks. Last in, first out. Pushing, popping. And they're easy to implement using a linked list, actually. It's quite common for people to do that. But if you think about it, the bottom stack or the bottom pancake on there, literally, if it's the first thing in, it's the last thing off. We can't access from the sides. We can only access from the top. We can't access from the bottom. We have to go this way only. So my question to you now is, if we pop all of the elements off a stack, so it's empty, and we pop again, what's that called? When you've got no elements on the stack and you pop again, what's that called? Ooh. Not Peak, no. Peak's just looking at it. Ooh. Well done. It is underflow. Perfect. So when you've got no elements and you try and pop, you get underflow. If your stack is full and you try and push onto the stack, what do we get then? Yeah. Overflow, excellent. Okay, good. And it's the same for a queue. You can get underflow and overflow in a queue as well. Now remember, these stacks can be implemented as an array, because all it is a sidewards array, remember? Here's some elements. We start at 0, 1, 2, and 3. Okay? If I asked you to push something onto a stack, just think about what has to happen for me for a second. Let's say I've got 14 and 16 on a stack, and I want to push something on a stack. Think about what operations have to go on to do that. We have to increment a pointer. So you have a pointer which is pointing at the top of your stack. We call that the head. What we would do is we would increment head by 1, wouldn't we? So this is me just doing it rough in pseudocode. Head equals head plus 1. That would then push head up to point at this position here. And then I would say head, or whatever the array is called. Let's say my array at the position of head is given the value of 32. And 32 would end up going in that position there. Okay? That is your push method. If I popped something off there, you decrement or lower down head by 1. So head minus 1 this time. And then you would say my array at the position of head equals null. Now when you think about the logic of that, usually what you would do is you would do this first. So you put that above that one, do this one first and set it to null, and then move the pointer down. Okay, remove the data and then move it down. So you've got to think about the logic. If you ask to push and pop, I've seen a few questions before, ask about the pseudocode of pushing and popping, and there we go. there's the pseudocode for doing that, pushing and popping. The only difference you'll find here is that this is actually in Python. So here you've got a subroutine, it's a procedure. You've got your array at the top. You've got another procedure down here called push, and you're going to give it the data you want to push on. So there's 14 pushing on, and where is the pointer top? So what's the top of your stack called? All right. This is just some test data, so ignore that. And that is how you push and pop from a stack. You don't need to program a peek because that's not covered in the spec, so you don't need to know about that. And a queue works in a very similar fashion. However, the first thing in the queue is the last thing. First thing in the queue is the first thing out the queue. Very traditional, like in a supermarket. You line up, and that's it. So all you got to do is think about how this one would work for a second. Your pointer front points at 0, so that's the front of the queue. There's 0, so that's the front of your queue. Everything that comes in is going to be put behind it. Now I wonder if you can spot a problem with this. Because think about it. Value is my queue pointer front. So if that's 0, you're going to put something in value. Well, at the moment, there's nothing in there, right? So there's nothing in there. So this wouldn't actually work yet. But if we wanted to push data on, we'd say 14, pointer back. So what's the back of the pointer? Well, it's 0 at the moment. My queue at the position of 0 gets data. So 14 goes in there. Pointer back equals pointer back plus 1. So then that would become 1, which means it's pointing at this position. 32 would go in this time if I change that to 32. So the push method works. When you pop in, pop would start at 0 and move its way back. So if I pop 14 off there, I could never put anything in that position ever again. The queue will move back on itself all the time, leaving all this space free as it moves back. Not very efficient. But there is something called circular queues to cover that. But we don't do them in this specification, so you're good. Now, trees. Binary tree structures are comprised of nodes. Sometimes they're called leaves, like a tree, and it links between them. So the links between them are called branches, or usually edges. Each node is made up of 2 others coming off it. That is a perfectly balanced binary tree. Why is it balanced? Because it's got the same number of nodes on the left as it has the right. Excellent. Balanced. Balanced is great for efficiency. It makes faster searching. Wonderful. So, binary trees are used to implement another data structure called a binary search tree. They look identical. However, a binary search tree comes with a number of methods. They're your traversals that I was talking about before. So they're identical to binary trees, but have additional constraint. The data on the left of the node must be less than the data in the node itself. So we know that L, this, will have to be less than L. All right. Now, if it was numbers, it'd be easy. If you converted the L and the P to ASCII numbers, then this would also work here as well. All right. One recommendation I would make is when you're dealing with trees and they've got letters in them, make sure you write out the alphabet. A, B, C, D, E, F, G, H, I. Okay. Now you know that if you're looking at Sam and Poppy comes along, well, Sam, Poppy is before S, therefore it's less than it, so it goes on the left-hand side. When Lucy came along, we looked at Poppy, L is before P, so that would go on the left-hand side, etc., etc. And that's how your binary search trees are made. All right. Now this instruction will be in the exam question, so don't worry about it. The question that you might have is, what happens if the nodes are the same? So what happens if these are the same thing? Well, if you had Poppy and Peter, you'd move to the second letter and check the second letter. Then you move to the third letter. If they're identical, the exam question will tell you what to do in that case. All right, they'll tell you what to do if you've got an identical match normally. All right, so that's a typical question. You've done these in class. We're not going to go through it, but you basically look at it and you say, well, Phillips is my root node or the middle element. So that's like our Sam there. That's the root node. And then after that, S. So does S become S comes after P, therefore it would be on the right hand side of Phillips. Then you go Blackpunt. All right, Blackpunt would go to the left of that because it's B. All right, and so on and so forth. There you go. Right then. So let's look at our traversals for a second. You did this before. You start at the root node, node left and right, and then for a pre-order traversal, you take the node first and then you traverse left and right. For our in-order traversal, you put L and R above the nodes and you search left first, then you search left first, then you do left, there's nothing there, then you take the node itself, so you'd write that down, and then you would look right, nothing there, you go back, you've done left, so you tick that off, you've got the node in the middle, which you take down there now. If you want to mark every time you do traversals, pre, in, and post-order traversals, in a pre-order traversal, the root node should be first in the list of letters. In an in-order traversal, the root node should be in the middle of your letters. In a post-order, the root node should be in the end, the last letter. Okay? Again, watch my videos on traversals if you need extra help on those. Okay? All right. So we'll skip on past that using the pointers. Actually, let's not skip on those because these are common questions that students really, really struggle with. In the chat, has anybody seen this question before? Anybody seen this question before? It says a binary tree can be constructed using the following rules. The first item becomes the root node. Items earlier or at the same position in the alphabet follow the left pointer. Items later follow the right pointer. Draw a representation of a dynamic binary tree with pointers using the following data. Newport, Canterbury, Oswestry, Warrington, Rugby, Bath, Derby. 2 marks. Show how the above tree could be represented using a 2-dimensional array. Now this is tricky because 2-dimensional array, remember, is just rows and columns. You're going to have the left pointer, the node, and the right pointer. The top position starts at 0, down to whatever number you're going to need. Okay? Newport is in position 0. Canterbury is in position 1, Oswestry in 2, so it goes in levels, people. Levels. Then, after Oswestry, you've got Warrington, Rugby, Bath, and then Derby. All right, so look at it here. What they've done is they've done Warrington was 3, Rugby was 4, Bath is 5, Derby is 6. Now it doesn't matter which number they go in as long as your pointers are correct. So Canterbury has a left pointer of 5. 5 is Bath. So look at Canterbury, look at the left pointer, it has a number of 5. Canterbury should have a right number of 6. Let's have a look. Canterbury, 6, right pointer. Yep, that's correct. So as long as your numbers are correct, you can't be penalised for how it's been drawn. All right, there's another example when it's changed. All right, removing nodes. If you have to chop a node off, you have to make sure that your pointer reference goes to the new node. There's an example. Linked lists. Very common because they're dynamic and they expand and contract really easily and they're good to edit. linked lists have two parts to them, the data and the node itself, the node pointer, right? Data and the pointer. So unlike arrays that can grow to whatever size required, think of it like a train. You've got your engine at the front and all the carriages are connected with a pointer, so some kind of locking mechanism. So Sam, Peter, Emily and Edward, you've got them all connected. Edward is the last node on there which connects to nothing, right? If I decided to slice off this here, yeah, Emily and Edward would never be able to communicate with Peter and Sam again because they've broken the connection. And if you did this on a train, these carriages would float away off into the abyss. All right? So there you go, data and a pointer. Now if you think about it, when you add a new node, you're trying to put Dan in there. Now remember, when you're adding a new node, it has to go wherever the last pointer is, because this is going to be the tail pointer. Right? Got to go in the last place. If you're trying to edit something or adding a new node in a specific position, you'd have to find the Emily position, change Emily's pointer to Julie's, change Julie's to Peter, and carry on with your life, and then sever that later on. Okay? Typical exam questions these. You can remove it just as easily. Take Julie out. Make sure you connect first before you sever. You can't destroy these until you've made the connection, otherwise they'll float away. Finally, the last data structure is hash tables. Very, very fast retrieval of data, no matter the amount of data that is stored in them, and that's why they are popular. Now, they're very fast because they store data in what we call an associative array, so key value pairs. If you've done Python before, it's like a dictionary. It uses a hashing algorithm. Have you heard of a hashing algorithm before? Hashing algorithm? Data. This is your hashing algorithm. And this gives you the location. I always draw this diagram. Data goes in. The hash, who knows what that is? Nobody knows. The only person writing it would actually know what that is. So data goes in, let's say John, and my hash was len. What's the length of John? And then location would be location 3 because it's 3 letters long. Okay? That's a hash. So when index is generated, it's always numeric. So that's this. Index is location. That's always numeric. And the hash table provides direct access. So it's the fastest way to find the location of your element in the array. That's why hashes are used. So there's a hash table. Index, name. So to find someone like Lou, using linear search will take a very long time because we'd say, are you Lou? No. Are you Lou? No. Are you Lou? No. Are you Lou? Yes. Well done, we found it after 4 searches. If we know the index, we can find the position in the array almost immediately, or direct access. So we might say, if we knew that Lou was in position 3, we'd just go straight to Lou and say output whatever's there. That's what we're trying to achieve. So we put data into the hashing algorithm. It tells us the location in the hash table. So the hash table, if you have to draw one, has 2 parts to it. A table where the actual data is stored, and a mapping function, which is what your hash is. Your mapping function is called the hash function in real life. All right? Okay. So hash tables, what problem do we have? What if 2 items or 2 locations clash? Well, collisions are a bit of a nightmare. So this, if you've seen it, this came in file handling. So when we have like data files, each block has a maximum record count. So when we're storing this in a file, here's my file. We split it into blocks. As we add data in, the blocks become more full. Oh no, they're full. We can't add anything more in. What do? We have to create an overflow area to stick anything in there that we might need. Or we can get rid of that, change the hashing algorithm, or create a completely new file with much bigger blocks. and we can store way more data in there now. Happy days. So they're the two methods of getting around that. Two types of overflow when it talks about hashing. There's progressive overflow, which is if the location is occupied, then use the next available location. If the end of the file is reached, wrap around and we start searching from the beginning again. So we basically keep checking the block to see if there's any freed up space, or you can add a flag in the original block to move data into the designated overflow area. That's the most common one. You don't really have that problem because memory is quite abundant nowadays. Quite abundant. All right. Happy days. Okay, there's an exam question. If you wanted to pause the video there and have a go, that's absolutely up to you. Okay, let me skip back to the start. There are questions and mark schemes in here to allow you to actually practice this. Okay, what's that now? Is anybody still there? Have I just been talking to myself for an hour and a half? I don't know. Who's still there? I think we'll round off with some exam questions. You've got all this content anyway, which is great. Thank you, John. I'll skip on to some of these questions and see if you fancy a final question. A final question. It's 20 past. We'll aim to finish at 8:30. We've got a translator question, reserve word and identifier table. So that's the first one. We've got two of those that you could do. We've done the big old one. We've done the back as no question. We've got a dry run algorithm. Dry running algorithm. Some pseudocode to tackle. So that's really dry running, but for testing, I suppose. You've got an object-oriented question. We've been through the theory of that, though, I suppose. We've got an inheritance question. Some Boolean Algebra. Boolean Algebra is definitely going to appear, by the way. Boolean Algebra question. Compression. Data structures. Two legislation questions. What do we fancy? What do we want? What do we want, people? You tell me, and I'll do it. What do we want? Do you need to remember the pseudocode for all the sorts and searches? I'd say yes. But I would say make an educated guess about which one you're going to need. With the sorts and searches, you've got to remember, if you've got a great memory, then well done you. But think about what they're asking you when it comes to pseudocode. There's always going to be inputs of data. There's always going to be outputs of data. There's always going to be selection. There's always going to be sequence. So selection is if statements. So sequence is code following top to bottom. And you've also got iteration, which is looping. They're always going to ask you to do some mathematics, so that'll be some adding up of some kind, subtraction, division, modulus and div operations potentially, sums, means, modes, averages, that kind of stuff. So I would say, I remember a bubble sort. Bubble sort starts at position 0, works its way consecutively as an outer loop for passes and inner loop for swapping. So I might remember the swapping mechanism if I don't remember the whole thing. Insertion sort starts at position 1 and works its way backwards, but builds a sorted list as it goes. Quicksort is a recursive algorithm which calls itself within itself until a base case or terminated condition is met. So you've got to weigh it up. If an insertion sort was on the last year, then that might be one that you might not want to look at potentially. Yeah, it is long. Yes, it is. I mean, what I would do is I'd go on ChatGPT and ask it to give you a simplified quicksort algorithm. It might be more beneficial remembering that. Remember, you can't be penalised for something different providing it works. So if you've got 6 different versions of a quicksort, there are many ways to program a quicksort. If you've got 6 different methods of programming it, all of them are completely valid. So, that's what I'd do if I was a studious student. Does anybody want any exam questions from that list there? Hey, if not, people, ho, if not, haha, we'll... Boolean Algebra. Right, one thing I'll mention about this, Mr. Wong. What? You're all right. Oh, okay. You're good. Excellent. Boolean algebra is definitely going to appear, and if you think about it, De Morgan's law is always going to be in there, isn't it? Always, because it's an A2 thing. It's an A2 thing, isn't it? Second year. You can't do Carnot maps on this specification, if you know what that is, if you're an electronics person. However, De Morgan's law is breaking the bar and changing the sign. That's as simple as that. So if I took this first one and I was like, well, what's this here? It's got a bar on top of it. It's asking me to actually do De Morgan's law. It's the only law it'll tell you to use. And this one just says Boolean algebra identities. There's so many. Okay? Those people that says it's 3 marks or how great they are, by all means, put the final answer in the chat for me. Breaking the bar and change the sign. Z. X. The bar is an OR. So I'm going to put an AND. Change the sign. Break the bar, break the bar, break the bar. I have now applied De Morgan's law. I have got 1 mark out of those 6 so far. Well done me. Yeah? That's the first step I'd take anyway. So what does that give me? Well, let me write it down here so it's nice and clear for you. That's still X plus Z ANDed with Z and X bracket split. Okay? Now at this point, you might not do this because you might not be as pernickety as I am, but if I do this and I write this here and I swap this one with a Z there, knotted. What I'll do now is I will expand. So I will multiply out each one against each the other. So I'll multiply that by that, and that by that, and then multiply that by that, and that by that. Okay? Multiply all of them out. What I'll do is I'll get X multiplied with that. There's a not X there. I'll get my X. I don't want to make a mistake here. Needs to be really careful. So that's X and Z. Is that one? So that X has done that one and that one. Then what I'll do is I'll get an OR and I'll get a Z and knotted X, and I will get a final Z and not Z. Okay, that's me expanding. Expanding will get you 1 mark. Happy days. Then you've got to think about, right, well, what can I cancel down? Well, if you and anything with the not of itself, there'll always be a 0 somewhere. So that will result in a 0. Then I've got X and Z. Still nothing. I can't do anything there. I can't do anything there either. Z and not Z again. That'll be 0. Okay. Then what you've got to do is think, well, anything, oh my goodness, anything ended with 0 is just going to be 0. Like, you're going to lose all that. And same on this side, 0. So you got 0, 0. That was easy. The answer was 0. That was easier than I thought. I hope I'm right. Nobody in the chat put the right answer. Nobody even attempted an answer. You're all weak, scared. So yeah, there we go. Now what you can do is we can look at the other one. Just get rid of all that ink for you a second. The second one doesn't have any De Morgans in it because there's no knotted bars, I suppose. But what we can do here is select my pen. Push. And the first thing I would look at is thinking, well, I've got A or C in this bracket and A or C in this bracket. So I might consider the fact that I've got 2 of those. And if you've got a cat or a dog, and you've got a cat or a dog, well, guess what? You've got a cat or a dog still. So I can cancel one of them down, I think. So I'd probably go down the route of B and A or C and A. Yeah, so I'm keeping this one, I'm keeping this one, I'm keeping just one of these. Then what I'll do is couldn't you do absorption for A or C? Yeah, you could do absorption, yeah. You could do that absorption straight away. There's I think there's there's a few ways you can do this actually. There's a few ways. What I would do now is I would swap this around, put that there with that. So this is the commutative law. Commutative law means you can swap around anything you like really around your expression. And like Namir said there, I could just do absorb there. If you didn't know how the hell I got that there, that absorption, what that actually means is if you multiplied this out, you'd do A and A or A and C. This one's going to cancel down to A, isn't it? And then you've got A or C. And then anything ANDed with itself is itself. So if you did A and C, it just becomes A, doesn't it? Which basically cancels down to this, cancels down to that. That's why you get A. So that's the proof there of absorption law. There we go. That's the proof anyway. You don't get asked to do the proofs. You just have to show it really. So yeah, the answer to that is just A and B or B and A, whichever way around you want to do it. Both are acceptable. And that is Boolean Algebra. If you didn't know how the hell that works, think about how you could access some of the marks. Can you expand any brackets? Can you use some of your identities like A and A or A, for example, to try and simplify anything down to get some marks rather than none? That question there, again, is from the 2023 paper, I think, and it's worth 10% of your paper. So, Namir, if you don't get all your marks, I'm going to get your paper back. If you don't get all the marks for that question, we're doomed. We are doomed. Okay? Right, people. What did we cover? Translators and Big O, we did those. Dry running, we didn't touch. The compilation process, compilers and interpreters, we did. Compression, we didn't do. Legislation, we didn't do. Data structures, we did. We touched on Boolean algebra and we looked through the object-oriented paradigm, but not the other paradigms. But we quickly, people were telling me that they knew what they were. All right. So this is the end of the Component 1 live stream. Again, if you have any questions, fire them through. I'll put these up onto our Google Classroom for you so that you've got copies of it. It'll be a PDF, so you can just click it and go straight to it. So it's all a sort of a PDF, nice and easy to use. I'll put the mark schemes in actually for the questions at the end because I don't think I did that. No, I didn't. No, I didn't put any mark schemes in. I'll put the mark schemes in for you so you can have a look at it. And let me know what you want for component 2 and also when you want it as well. That'll be quite important as well. All I can do now is wish you the best of luck. Like really, what you do now is vital to what goes on in the exam. Have a steady revision process. Make sure you give yourself breaks, plenty of breaks, because you don't want that cognitive overload. Revisit things. Try and chunk them down. Repetition's a great thing. Don't just reread your notes. Remember that academically, that's not proven to be very useful. Don't highlight things. Again, that's not academic. That's not proven to be very helpful. You need to reread your work, create mind maps, flashcards, small, low stakes testing. Right? Get on the AI. Get on ChatGPT. Upload a document now. Ask it for some questions. Ask it to quiz you, and it will. Contact your rest of your mates on our course. Get them to come into college. Use the know. Sit in there. Quiz yourself. What you do now makes a massive difference. So get on it, people. And I wish you the best of luck. I hope that you do excellently well, and you get to where you need to go. All right, people. If there's nothing else, if there's no more questions, I will disappear into the ether. I hope you found it useful. I hope the time was spent wisely. All the best, people. Goodbye.